to vote.
Okay. Dummy bastard, ain't it?
So that's max load there for a 15.
That's max load. I mean, that's a 15 loaded right to the max, footage-wise. Alright, so, let me grab the scope.
So where does that hum come from? The buzzing?
That's capacitance from the glass of the table. Okay. Like when you feel the tubes, you can feel them.
Yeah, I felt a little corona on it.
So let's go up to, what I'm going to do, because I don't want to particularly hold this, I'm going to clip it on here. And then will this reach? No. We'll extend it slightly. So I'm just going to measure one side to ground. This is the waveform across the glass. So instead of the normal sinusoidal thing you'd see, when you run it across neon, you get this effect. You can, basically it squares it out. Once the gas fires, it maintains a constant voltage across the tube until the voltage gets, when the transformer gets low enough, it extinguishes, it goes out, and then you get the second half of the cycle. The part here that's significant is this ringing stuff right there. What happens is the voltage out of the transformer starts coming up from zero, the tube is off, and you reach a point where the tube ignites. Neon has a characteristic that once the tube ignites, the voltage across the gas will drop by a fairly significant percentage, which is a very sharp transition voltage-wise. You combine your wiring inductance, transformer inductance, and capacitance from all this glass against the table. I put my hand on this to change now. And you form a resonant circuit. And so that fast drop in the voltage causes all this capacitance inductance to start circulating energy back
from
and forth.
From lamp.
And it rings. So you get this ringing waveform. Eventually, it dies out and you get a nice on transition like that. Now, this ringing waveform is what kills the trannies. As you can see, it's not very significant on this one, but you can see that, you know, because it's ringing, you get voltage peaks above and below. So it adds to the normal operating voltage. Okay, that's all well and good. Now, and this is, you know, how you do not want to load your trannies. This is about, what, 20 feet of flex per leg. Alright? We'll take our tranny. Now this is a guy doing a letter install at a shopping center, and he's got his trannies remoted 20 feet back into the crawl space. And so he doesn't care. You know, he just slaps it up there.
You just make sure it lights before I
Fires
leave.
it up, it lights up when I left, and ship it, and we're out of here. Okay.
Where's my check?
Where's my check? So, not going up on this sort of thing. He decides he's done it before and it didn't fail immediately. This over here. Get in there. Make a little space here. Place those back in. Hook up our high voltage probe. We can see what's going on. Now, notice that waveform change?
Oh.
Now you've got 10 kV spikes on a secondary hub that's only supposed to max out at 7.5 unloaded. And it's constantly ringing. In fact, you can see the glass flicker.
Yeah.
And that's just by adding, you know, two 20-foot runs of GTO and flex.
40 extra feet.
40 extra feet. And you can hear it, I mean, and you can see it. And if you run this long enough, it'll eventually fail the tranny. Because now you're putting 5, 10, 20 kV across a 15 kV tranny. And you can see, now notice when it first starts, if you flash on that, you can see the sine wave before the stuff strikes. Right? So compare that waveform with all of that crap versus what you get without the GTO inside 20 feet or 40 feet of flex.
Wow.
So not only can you hear it, you can see it. So when you go up to a sign that's making that buzzy noise, you can envision it doing that. And, you know, without that, you know, I was measuring, well, what would we expect? We got 7,500 sides, we expect to see 3,750, right?
Yeah. Okay.
And let's just see what the voltmeter says. So this is showing 4 kV a side. But the scope is showing 10 kV spikes. So what this shows is, even measuring with a voltmeter, you won't see what's really going on, because basically the high voltage probes and meters were originally designed for measuring DC. We found that they would run with AC, but they will not measure the high frequency. They'll measure the average. So what they're measuring is, this is 5,000 volts per division. So 5 kV is that line right there. So basically it's measuring that average line right there. It's not measuring the peaks, which are double that.
Okay.
Alright. So for every peak that goes to there, there's another peak that other end goes down towards 0. So the average is right in the middle. So even though our meter is showing that we're properly loaded, you know, in the ballpark, we expect 3,500. That was showing, you know, 30. What did I say? 30.
You say 38?
38. Anyhow, so we're slightly, technically we're slightly over. But what it's not showing me is the 10 kV spikes. So let's go back. This is a sanity check. We'll take this back out. Plug that sucker. I get to talk and then reach over and hit the switch accidentally. While it makes for an impressive demo, it's not the demo you want. Me doing a triple backflip across the garage is
hey, it'll make ratings.
And this is what, 1 foot, 1.25 foot jumper to right to the tranny.
The ideal installation for
the
this.
ideal installation. Firing it up, point. And you can see the difference. That's nice and clean. Now we still have that because we're pushing the edge of the envelope with this amount of tubing. In fact, let me take out a couple and underload this. Let's just run, let's see, 1, 2. Now let's just jump. We'll take it down to 4 tubes instead of 6. This is severely underloaded. Smaller and tighter. Alright. So let's go one more step. Let's go half a load on a 7,500 volt tranny. This is a non-SVGA tranny, which is worth its weight in gold these days because you can't get them anymore. You won't see them anymore. And what they're really useful for is debugging. Get a sign and they go out there and the thing's resetting and driving you crazy.
Oh, because the the chip there.
Yeah. So you say the heck with this. They put the ground on the other end. You grab your handy non-SVGA tranny and pop it in there. And now the sign stays on. You can walk in and debug. figure out what's going on. Look, this probes with these nice long wires on it. Just hook that to the ground. Now we're running half the tranny, so we'd expect to see half the voltage. Oops. Wrong knob. There we go. Yeah. It's not a whole lot better. Probably because I got all this 14-gauge house wire, so we don't want to grab that. That's actually slightly worse. Interesting. Now that's 2, 4, 6. Spiking to 6 kV. Huh. I'll even it out, this goes to show. So instead of running 2-foot feeders, I'm now running 6-foot feeders, or 4-foot feeders. How long are those things? Maybe 4 to 5 foot. Not in flex. That's just open air. I'm still getting a good sized ring on a red tube. Interesting. Then you would have with a 15. Still pretty spiky. 2, 4. Centered. Now we get it longer. 2, 4. So we got 4 kV spikes and about a 1.8 to 2 kV operating voltage. So our ringing is still there.
Yeah.
With a smaller tranny. But if we're wiring with, GTO 15 kV GTO, even with the spikes we're hitting 4 kV rather than 8. So while the tranny may not be happier because it's all a red tube load, the GTO will be happier.
Yeah.
It's under less voltage. Alright, let's go one more. Throw a couple of blue tubes on here and look at the difference. Yeah. So all that's, the spikiness, we've still got a little bit of ring here. I think I actually got more than I would have expected. But you can see the voltage is a bit lower. It's, nice soft middle section there. If I just turned up a notch. There's still a little ring there. Interesting. Not sure why that's there. But anyhow, you can hear the difference.
Yeah.
Okay. Power switch. Yeah, still got a little ring to it. Interesting. Huh. Okay, well, be that as it may. That's a 60 mil tranny rather than 30, so we're
Oh, it is also 60.
So we're pushing our little electrodes there a bit, but they can take a joke. Now just for fun, because we have this tranny, I should be able to add my capacitance. This adds 3,600 picofarads. You can't get that much GTO. That one is so bad you can't even see the waveform. Here, I got it stable. That's a blue tube under 3,600 with 3,600 picofarads of capacitance on a 7,500, underloaded by a third because I've got 2 tubes instead of 3. And I am getting 2 kV spikes, which still isn't bad. So that's a blue tube. I'll bet you on the red tube it'll be bloody impressive. But since we have red tubes, let's try it. First, again we're going to be underloaded. 2 tubes instead of 3. Oops. Gotta hook the scope back up. That's the trick there. Okay. Turn that down a little bit. Turn the brightness up so I can actually see the bloody thing. Stop it. Oh, trigger on there. So there's our, that's not a bad looking waveform. Actually looks a little even better than the blue one, to tell you the truth. Okay, so there's our reference waveform. There. So, actually see it start to arc over.
Yeah.
So that's adding a whole lot of capacitance to a red tube. And you can see it, and this is 2 tubes on a transformer that should load 3, and you still see they're still flickering. You can see all the arcs and sparks there. So, bottom line, capacitance bad. You want to avoid it. However, and you see, actually they're brighter.
Yeah, that's it. Is
that true? Yeah.
Yeah.
See how the discharge has gone down into the center of the tube? So, same glass, same tranny, only one variable, and that's the capacitance that we're playing with. So, if nothing else, this should convince people, you know, seeing something like this, that you really want to use center feed. Keep those runs from the tranny to the glass as short as you can get them.
And the virtual.
And then virtual, and then tie the 2 ends together, because that's roughly 0 volts. So you can run a ton of that, you know, 0 volts through, you know, all the capacitance you want. It's still 0 volts to ground.
Yeah.
So the effect, you know, is even though the capacitance is larger because you've got all this wire inside this length of flex, the effect is negligible because there's no voltage, which is why virtual works. And if you're hardcore and get a perfectly balanced side, you go with midpoint return, but that's sort of, you know, almost a kind of a why bother.
Yeah.
You can see it's a little deceptive what we're looking at here. Let's see, can I get a line sync? Where's the line sync? There's the line sync. And phase. Stop. 2 phases, yeah. Okay. It's a little hard to see what we're looking at here, but here's 0 right on that line. Yeah, it actually makes it worse. And then the dimmer turns on, it rings, the line voltage goes back through 0, but the current is still flowing because the transformer is inductive. So you see the voltage will actually go back through 0 and then or back through to the negative polarity, then it'll come back to 0. And as you change the dimmer, what you're doing is you're changing the width of that on time. So there's on time from there to there. This is the off. This is off time from the previous waveform. So you turn it all the way up, you get full waveform. You turn it down, you go to 0. Now, the inductive load, it's kind of really hard to tell. If I put a resistive load on there, you get a nice clean waveform. But, as you can see, the one downside of running dimmer is that voltage spike right there. Let's see, where are we? Blank. 2, 4, 6 kV. So I got a 6 kV voltage spike there on ignition. And the size of that spike varies as a function of, you know, how much dimming you've got. When it's lit all the way, it's only about a 5 kV spike. So, running partially lit red sign on a dimmer is actually slightly harder on the tranny voltage spike wise.
Because you're going to have to change the transformer, right?
Well, typically what you do, most people what they do is when they're running glass work with a dimmer, they're underloading the tranny anyhow. So by having less glass on the tranny, you know, they're covering that voltage spike problem. If you're running a full load on a tranny, especially if I was dimming a 15 with a full load on it, you get some nasty voltage spikes at partial load. And it's not the load on the tranny that's going to kill it, it's those stupid voltage spikes that are sitting there punching at the insulation inside the tranny trying to arc over. Once they arc over, then you got a carbon track and you're toast. And it's kind of impressive. What I got laying around that doesn't burn very well. I guess I could do this on metal, but here's a big ugly steel plate. This will work. Okay, so the question becomes, what happens when GTO fails? Well, the way to find out is fails in GTO and C. So we're going to take half of our tranning here. Yep, need a little more, don't look at that. I'm going to lay it on the steel plate just so I don't set anything on fire. And then I'm going to take the wire here from a ground. Solve that problem. Okay, so we got an arc. So when your GTO fails, you just lay that right on there. So here we are, burning away our GTO. It's a pretty good fire going there. Now, let's see what we got. See this? Well, I got a little crap. What is this? Technolux? X. Huh. Anyhow, normally if you do this with a regular piece of GTO, it'll turn to carbon. With silicone GTO, it turns to glass. So there's no carbon tracking on that. That's one of the big advantages of silicone over a regular GTO. Is if it does arc, so we just got something that's right on the edge. It's going arc, every once in a while. With regular GTO, it'll form a carbon track, and it'll get worse effective.